In our first lecture, we have discussed on the idea of estimators for a given parametric function. But in practice, there are so many estimators for a given parametric function. In the present lecture, we shall discuss different criterias for choosing a good estimator. Firstly, we shall discuss how one can compare two estimators on the basis of their closeness around the unknown parametric function. Next, we shall introduce the idea of the mean squared error of an estimator. Then we shall discuss the idea of unbiasedness of an estimator. Finally, we give some examples where we see that the MAC of a biased estimator may be smaller than that of an unbiased estimator. In this lecture, first we shall discuss the concept of estimable function. A parametric function g theta is called estimable if there exists at least one unbiased estimator of g theta. Consider the following examples. Example 1. Suppose x follows binomial n, theta, where n is known and theta is unknown. Let g theta be an estimable function of theta. Then there exists a statistic t such that expectation of t under theta is equals to g theta for all theta belonging to the interval 0, 1, which implies summation over x from 0 to n tx into ncx into theta to the power x into 1 minus theta whole to the power n minus x equals to g theta for all theta belonging to the interval 0, 1. We write this equation as 1. Since the LHS of 1 is a polynomial in theta of degree n or less, therefore to hold the identity, the RHS must be a polynomial in theta of degree n or less. Therefore, if x follows binomial n, theta, then the estimable functions of theta are polynomial functions of theta of degree n or less. Note that the functions 1 by theta or e to the power minus theta are not estimable because they cannot be expressed as a polynomial in theta of degree n or less. Consider another example. Suppose a random variable x takes only two values 1 or 2 with respective probabilities theta square plus theta cube and 1 minus theta square minus theta cube, where the unknown parameter theta can take only two possible values 1/3 or 2/3. On the basis of a single observation x, suppose we want to see whether the function 1 by theta is estimable or not. If possible, suppose 1 by theta is estimable. Then there exists a statistic capital T which is an unbiased estimator of 1 by theta. Hence, expectation of t under theta is equals to 1 by theta for all theta equals to 1/3, 2/3, which implies t1 into theta square plus theta cube plus t2 into 1 minus theta square minus theta cube is equals to 1 by theta for theta equals to 1/3, 2/3. Thus we get the following two equations: 4 by 27 into t1 plus 23 by 27 into t2 is equals to 3 and 20 by 27 into t1 plus 7 by 27 into t2 equals to 3 by 2. Solving these equations, we get t1 equals to 27 by 32 and t2 equals to 27 by 8. Hence, there exists an unbiased estimator of 1 by theta. In other words, 1 by theta is estimable. Consider another example. Suppose x1, x2 up to xn be IID normal mu sigma square variables, where mu and sigma square are both unknown. Here theta is a vector valued parameter which is equals to mu comma sigma square. Let g theta equals to e to the power minus mu plus sigma square by 2. We want to see whether g theta is estimable or not. From the MGF of normal distribution, we get expectation e to the power tx equals to e to the power t mu plus half t square sigma square for all theta and for all t. Setting t equals to minus 1, we get expectation e to the power minus x is equals to e to the power minus mu plus sigma square by 2, that is g theta for all theta. And hence expectation under theta 1 by n summation over I from 1 to n e to the power minus xi is equals to g theta for all theta. And hence there exists an unbiased estimator of g theta. Therefore g theta is estimable. Now we shall discuss the concept of linear unbiased estimator. Let T1, T2 up to Tk be k unbiased estimators of g theta. Consider a linear combination of T1, T2 up to Tk, namely T equals to summation I from 1 to k Li Ti, where L1, L2 up to Lk are real numbers. For T to be unbiased, we must have expectation of T equal to g theta for all theta. This implies summation over I from 1 to k Li into expectation of Ti equals to g theta for all theta, which again imply g theta into summation Li equals to g theta for all theta, which implies summation Li equals to 1. By equating the coefficients of g theta, such an estimator T is called a linear unbiased estimator of g theta. It is natural to look for an estimator which is based among all linear unbiased estimators of g theta. If such an estimator exists, then it is called the best linear unbiased estimator or BLUE of g theta. Thus, an estimator T will be called the BLUE for g theta if it has the minimum variance among all linear unbiased estimator of g theta. Now we discuss how to determine a BLUE. For the sake of simplicity, we assume that TIs are independent. Let variance of Ti equal to sigma I square for all I equals to 1 to up to k. Then the variance of T is given by summation over I from 1 to k Li square sigma I square. Now our problem is to minimize summation over I from 1 to k Li square sigma I square subject to the constraint summation Li equals to 1. To solve the problem, we consider the Cauchy-Schwarz inequality. By Cauchy-Schwarz inequality, for any two sets of real numbers a1, a2 up to ak and b1, b2 up to bk, we have summation over I from 1 to k ai square into summation over I from 1 to k bi square is greater than equals to summation over I from 1 to k ai bi whole square, where the equality sign holds if ai is equals to some constant c into bi for all I. Now setting ai equals to li into sigma I and bi equals to 1 by sigma I for all I, we get summation over I from 1 to k li square sigma I square is greater than equals to 1 by summation over I from 1 to k 1 by sigma I square, since summation li equals to 1. The minimum value of variance of T is equals to 1 by summation over I from 1 to k 1 by sigma I square, and the minimum is attained if Li into sigma I square equal to C for all I, which implies that Li equals to C by sigma I square for all I. Using the constraint summation Li equals to 1, we get C equals to 1 by summation over I from 1 to k 1 by sigma I square, and hence the BLUE for g theta is given by summation over I from 1 to k Ti into Wi whole divided by summation over I from 1 to k Wi, where Wi is equal to 1 by sigma I square for all I. Therefore, Wi's are equal to the reciprocal of variances of Ti's. Note that if variance of Ti equal to sigma square for all I, then the blue for g theta will be summation over I from 1 to k Ti whole divided by k, which is the simple arithmetic mean of Ti's. Finally, we shall discuss some drawbacks of unbiased estimators. The first drawback is an unbiased estimator may be inadmissible. Consider the following example. Suppose x follows Poisson with mean theta and g theta equals to e to the power minus 3 theta, where theta greater than 0. Let Tx be an unbiased estimator of g theta. Hence, expectation of T equals to g theta for all theta, which implies summation over x from 0 to infinity Tx into e to the power minus theta into theta to the power x whole divided by x factorial is equals to e to the power minus 3 theta for all theta, which implies summation over x from 0 to infinity Tx into theta to the power x by x factorial is equals to e to the power minus 2 theta, which is equals to summation over x from 0 to infinity minus 2 whole to the power x into theta to the power x divided by x factorial. Comparing the coefficients of theta to the power x by x factorial from both sides of the above identity, we get Tx equals to minus 2 whole to the power x for all x, and hence Tx equals to minus 2 whole to the power x is the unique unbiased estimator of g theta. Here, T is inadmissible since g theta is a monotone decreasing continuous function of theta taking only non-negative values, whereas T is an oscillatory function of x taking both positive and negative values. The second drawback of the unbiased estimator is that there may not exist an unbiased estimator in all the cases. Let us consider the following example. Let x be a random variable with PMF. Fx equals to 1 minus theta whole to the power x into theta, where x equals to 0, 1, 2 up to infinity and 0 less than theta less than 1. Suppose our object is to find an unbiased estimator of theta. If possible, suppose Tx be an unbiased estimator of theta. Then expectation of T under theta is equals to theta for all theta, which implies summation over x from 0 to infinity Tx into 1 minus theta whole to the power x into theta is equals to theta for all theta, which implies summation over x from 0 to infinity Tx into 1 minus theta whole to the power x is equals to 1 for all theta belonging to the interval 0, 1. Such an identity cannot hold since the LHS is a function of theta but the RHS is independent of theta. The next drawback is an unbiased estimator may not be unique. Consider the following example. Suppose xi follows IID rectangular 0, theta I from 1 to n independently. Now, if we define x bar equals to 1 by n summation I from 1 to n xi, then expectation of x bar equals to theta by 2 for all theta, and hence expectation of 2x bar is equals to theta. Therefore, 2x bar is an unbiased estimator of theta. Another unbiased estimator of theta in this example can be obtained as follows. Suppose x ordered n is equals to maximum of x1, x2 up to xn. Then expectation of x ordered n is equals to n by n plus 1 into theta, and hence n plus 1 by n into x ordered n is an unbiased estimator of theta. Thus, in this example, we get two unbiased estimators of theta. One is 2x bar and the other is n plus 1 by n into x ordered n. Thus, in this example, we get two unbiased estimator of theta. One is 2 into x bar and the other is n plus 1 by n into x ordered n. Another drawback of an unbiased estimator is that an unbiased estimator is not invariant under a transformation. That is, if T is an unbiased estimator of theta, then GT may not be an unbiased estimator for G theta. Consider the following example. Suppose T is an unbiased estimator of theta and GT is a convex downward function of T. Then, by Jensen's inequality, expectation of GT is greater than equal to G of expectation of T, and hence expectation of GT is greater than equal to G theta for all theta. Therefore, GT is a biased estimator of G theta with an upward bias. If GT is a concave downward function of T, then expectation of GT is less than equals to G of expectation of T, and therefore expectation of GT is less than equal to G theta. Therefore, GT is a biased estimator of G theta with a downward bias. We shall now discuss a practical example. Consider a coin with probability of getting a head in a single toss is equal to theta, where theta is unknown. Suppose our problem is to estimate 1 by theta unbiasedly. Here we apply the following inverse sampling methodology. The coin is tossed repeatedly until a head appears, and the experiment is performed independently for 20 times. From the outcomes of 20 trials, it is found that the first head appears in first, third, fifth, first, second, first, third, seventh, second, fourth, again fourth, eighth, first, third, sixth, fifth, second, first, sixth, and second toss. Let xi be the number of trials required to get the first head in the ith trial, I running from 1 to 20. Then the PMF of xi is given by fxi equals to 1 minus theta whole to the power xi minus 1 into theta, where xi can take the value 1 to up to infinity and 0 less than theta less than 1. Then expectation of xi is equals to summation over x from 1 to infinity x into 1 minus theta whole to the power x minus 1 into theta, which is equals to 1 by theta for all I. Hence, expectation under theta 1 by 20 into summation over I from 1 to 20 xi is equals to 1 by theta for all theta, and therefore summation xi by 20 is an unbiased estimator of 1 by theta. Now, from the given data, we have summation xi equals to 67, and hence an unbiased estimate for 1 by theta is given by 3.35. It is to be noted that from the third drawback of the unbiased estimator, here it is not possible to find an unbiased estimator of theta from the above data set. In the present lecture, we have seen that if T1 and T2 be two estimators of a given parametric function g theta, then T1 would be closer to g theta than T2 only if the MAC of T1 is smaller than that of T2. Therefore, MAC is a very important criteria for choosing a good estimator. But we can't compare two estimators only looking at their MACs. So we require another condition which is called unbiasedness. Finally, we have seen that in some cases, the MAC of a biased estimator may be smaller than that of an unbiased estimator.